A bright object like a flashlight right up to your face will certainly make you squint. But if you take the same bright object and place it a few meters away, it's not going to make you squint anymore, right? So how is it that I'm not any brighter right now than I was back there? So what's going on here? And what even is brightness? Humans have created artificial light, like fires, for longer than recorded history. So we instinctively know that, for example, reading a book under a lamp would be much easier done right next to the lamp than far away from it. So how is it that, from one's perspective, that objects that are near you, like these bushes in the foreground, are the same brightness as objects that are far away from you, like these trees in the background? So something does not make sense here, right? One part of our experience tells us that as objects are closer to us, they appear more bright, like you squint more with like the flashlight example. But the different part of our experience tells us that if you're looking at the landscape, it doesn't matter what distance things are. They're all going to appear the same brightness. So that raises the question, what even is brightness? Well, we have specialized cells in our eyes that collect light, that stimulate the brain, which translates to brightness. So this is what most people probably refer to as brightness. More photons hitting your light-sensitive cells in your eyes equals brighter images. And it just so happens that the distance to an object is inversely proportional to its brightness, which means if I hold a flashlight right up next to my face and then I proceed to double the distance to the flashlight, it's going to appear a quarter of the brightness. This is called the inverse square law, and the reasoning is pretty simple. It falls out of geometry. And we know that light that comes from the sun scatters pretty uniformly off of everyday objects like trees, grass, and bushes. So how come there's a disconnect? The trees in the background are the same brightness as the bushes in the foreground. What's going on here? Just to illustrate my point further, here are 4 photos I took 1 meter, 2 meter, 4 meters, and 8 meters away from the camera. And you can clearly see I don't get any brighter or dimmer as I get close or far from the camera. Just to emphasize this, here's the photo from 4 meters away, adjusted to what we would expect the brightness to be. And this obviously goes against our experience. So again, what's going on here? So we went over how we perceive brightness, but how do scientists measure brightness? What is an objective way to measure brightness? In reality, this is not a straightforward question. Here are just a few of the ways and units scientists use. There's truly a dizzying amount of information here. But there's one unit in particular that a lot of these measurements use, and it's called candela. And the history of candela is actually pretty interesting. It involves a bunch of scientists trying to standardize a unit for brightness using whale fat, gas lamps, carbon filament lamps, freezing platinum, and finally, radiators. The interesting thing about candela is that it measures the intensity of light per unit angle, which means how many photons are we getting per unit angle. The reason this is interesting is because it ignores the size of the object. If we have our sun and we measure how much photons do we get per unit angle from our point of view, and then we make the sun smaller with the same brightness, then the measure of intensity per unit angle is going to be the same. This is actually called luminous intensity. The key point to notice here is that as you get far away from objects, they also get smaller. So if you're looking at a cityscape, notice as you drive further and further away from the cityscapes, the buildings in your point of view look smaller and smaller and smaller. So if we take a look at the inverse square law we talked about, that states every doubling of a distance you do from an object, you're going to receive a quarter of the photons from it. And we look at the rate at which objects become smaller in our field of view, we realize they become smaller at the same rate as the inverse square law. If we look at a cityscape and we double our distance, a specific building would be half the height and half the width, which means the area would be 2 factors of a half off, which would be a quarter. The area would be a quarter of the area it was. So by doubling the distance away from an object, you receive the quarter of the photons but the quarter of the photons are spread over a quarter of the area. And this is precisely the reason objects in our point of view don't get any dimmer as we get far away. And that's why we don't tend to perceive the inverse square law. We don't tend to perceive it. As we get far away from objects, as I get far away from these trees, they become smaller and smaller and smaller in my field of view, but I also receive less photons from them. So yeah, this is precisely the reason things don't get dimmer to us as they're far or near. I came across this as I was taking pictures and portraits of people, and I realized that when you take a measurement or you try to take a photo with your phone or with a camera, you don't change the settings based on how far away you are, as opposed to what you would expect after you take a first-year physics course and learn about the inverse square law. Pretty neat.